welcome back. I'm Mr. Chai. Today I'm going to walk you through a full paper on A-level further mechanics 9231. All right, now that is paper 33. Let's get going. All right, welcome back. This is our first question from the complete paper further mechanics 9231, paper 33, June 2020. All right. Okay, let's get started. Now, first of all, in the exam, of course, we have to read through the question and then next, try our best to visualize it as much as we can. Right? Now, a particle P of mass m is attached to one end of a light inextensible string of a length a here. Now, the other end of the string is attached to a fixed point O on a smooth horizontal plane. Now you can see that from the diagram that I have prepared here. Now the particle P moves in horizontal circles about O. Okay. Now the tension in the string is 4 mg here. Now our task is to find in terms of A and G. Now the time that P takes to make one complete revolution. Right. So first of all, the particle is labeled as P. Right now, it's attached to a string here. You can see that of inextensible string. So its length is pretty much constant. And then the other end is attached to the fixed point O here. The surface where the particle is actually revolving is smooth, so therefore there is no frictional force will be taken into account here. And then first of all, you have to recognize that this is circular motion, right? Now I'm going to show you how um, the mechanics would actually look like before we actually solve it using algebra. Okay. Now you can see that this is how it would actually look like. Okay, now let me play the animations here so you can see it. All right, so the particle would be moving in a circular motion. All right, it's a horizontal circular motion. All right, so therefore the horizontal component that is acting on the particle is just the tension of the string. And then the tension of the string here, I need to okay, now once you recognize how the visual mechanics look like, okay, now it's time for us to try to relate all those properties of the mechanics that we need to solve this problem. So first of all, it does say that there's a tension here. Okay, so the tension is 4 mg here. All right. Okay, and then bear in mind this tension is actually acting towards the center, and then this tension is the one that provide the centripetal force. Whenever you talk about circular motion, you must think of centripetal force. Okay, so the first idea is in the exam, um, uh, always look at what type of mechanics involved. All right, now this is types of circular motion. Therefore, you must think of now like centripetal force. Okay, centripetal force. All right. So whenever you think of all these, now try to list down first any formula that would involve here. So centripetal force most of the time is given by mv square over the radius of the circular motion. Or you could actually use Mr. Omega square here, where the omega is actually angular frequency, angular speed, or angular velocity here. All right, and then not only that, you try to list down others formulas relevance to V, the tangential speed, okay, or tangential velocity. Now, since the object is moving in a counterclockwise direction, now this v here is the tangential or linear velocity that you're talking at. you're looking at, sorry, right? So as the particle move up to here, then the tangential speed or the linear speed or linear velocity is acting in this direction here. So all this v is assumed to be uniform in our analysis, of course. All right. Now in the actual practical setting, the velocity might be non-uniform in this case, right? So there is a linear speed or linear velocity, and then omega is the angular velocity in this case, right? Now other formula involved, okay, so don't forget, other formula involved would be, so for instance, v is equal to 2 pi r over t, and then whereby omega is given by 2 pi over t, or you could actually use 2 pi f here, where the f is the number of cycle um, completed within 1 second. All right. So once you list down all the relevance formula, then we are ready to start to analyze it. Okay. Now we know that involves centripetal force. Now you have to ask yourself one very important questions. What is the physical force that actually provide the centripetal force? So the physical force we are looking at is, or the resultant force. What is the resultant force involved in this mechanics? So the only force involved, I would say horizontally in the horizontal plane, the only force that is acting horizontally along the plane is the tension. We are not talking about the vertical force that is acting on the particles. Of course, there is another vertical force that is acting um, on the object itself. In this case, which is um, the the weight itself. Right now, you're wondering, since there's only one component that's exerting a gravitational force downwards, okay, towards the particle itself, don't you think the particle would be falling then? No. In this case, we assume that based on the questions, the particle is moving along a horizontal plane. So therefore, there is another force which is known as the contact force, or in this case is the normal force. So the normal force and the weight must be the same in this case, right? So these are all the properties of these circular motions that we can extract. Whether they're useful or not, we are going to look at that, right? So I'm going to come back here. The resultant force. So first of all, the first thing you need to know is resultant force. Okay. Now, resultant force is actually given by Newton's second law, F net equal to, or the resultant force, net force in this case, is actually given by um, ma, mass multiplied by acceleration. Or in our case, the resultant is actually given by um, mv square over the radius of the circular motion. So the radius of the circular motion in this case is a unit. You can see that as a unit. Okay. Right. Okay. Now this is on the right hand side. This is the resultant force that's acting on the object in terms of velocity and acceleration. Okay. Oh yeah, I need to make one thing straight. Since I'm using A, based on these questions, the A actually represents the length. Now this A, I shouldn't be using A anymore. It will be very confusing, even though most of the time we are using A in this case. So maybe I can write as dv dt, a rate of change in the velocity, which is the acceleration itself, right? Now, next is you are going to discuss about the physical force that is acting on the object, the resultant force um, along the horizontal plane. Along the horizontal plane, we are not talking about the vertical forces there. So the resultant force along the vertical plane is just the tension. So there's no other forces acting on the particle in the horizontal direction. So therefore, tension must be equal to mv square over A here. Where the A, I need to make a remark here. Based on these questions, the A is the length of the circular motion. Okay. And then we are given the tension itself. So tension is equal to 4 mg. So I'm going to equate this. uh, A equal to 4 mg. All right, and then of course we're going to do a bit of simplification here. Now that way, the m can be reduced, so we have v square. Now I'm interested to discover the time taken to make one complete revolutions. Therefore, I need to make use of this formula here, the v. So I'm going to square that. That will be a 4 square. Okay, 4 square. And then what else we need? That will be the radius of the circle. So radius of the circle itself is a. That will also be a square itself, and then divided by t square. Okay, t square is the time period, which is the variable that I need to discover here. The time taken to make one complete revolutions here. All right. So basically, that is how it look like at this point of time. Right. So from here, I can simplify that further. I will get 4 pi square over t square. Okay, the a can be simplified. Therefore, I will get 4g over a then in this case. Right. Okay. Now from here, now the 4 can be reduced, of course, and then therefore, in this case, I can actually write it down as pi over t. So I can square root both sides here. Okay, and then finally, I will be able to obtain the time period. So the time period, which is given by pi over a over g. Right. Of course, the unit is second here, right? Okay, so there you have it. This is how we solve it using one set of the formula there. Right. Now next I'm going to show you how to solve it differently then. Okay, now I'm not going to erase off this, but I'm going to, oh yeah, maybe I'm going to erase it off. It's going to be a bit messy here. Right. Now secondly, I'm going to show you how to solve it using different formula in both. Right. Okay, now let's clean this up first. Okay. Now we are still using the Newton's second law here. The net force is still equal to this, whereby the tension is still equal to, oh yeah, by the way, I won't be using this formula that represent the resultant force. Okay, instead, I'll be using the second format of the centripetal force, which is given by mr omega square here. And then therefore tension is equal to Mr. Omega square. Right? And then from here, the same thing, Mr. Omega square is equal to 4 mg, doing a bit of uh, reductions. And then bear in mind the r that we are referring to here is actually equal to a. It's a bit confusing. In this case, don't confuse yourself with the a that represent acceleration and the a that represent the length here. Okay, so from here, I will be able to get my angular velocity square equal to 4 4g over a. Okay, all right. And then therefore I found that this is equal to 2g over a square root. Okay, all right. And then now that is the angular velocity. And but what I'm interested to get is the time period. So the time period, this omega is given by 2 over t here. Therefore, it should be equal to this. Okay, you can see that. Now, finally, of course, you will be able to obtain the time period, which is the same as this one here, unit second. All right. Okay, there you have it. The variety ways of solving these circular motions problem. Right. Now, I hope that is useful. I'm going to move to the second question shortly. Stay tuned. All right, our second question here. Now, a particle Q of mass m kilogram falls from rest under gravity. Now, the motion of Q is resisted by a force of magnitude m the mass, k is a constant, v is its instantaneous velocity, v meter per second is the speed of the q at the time t second, and k is the positive constant. All right. Now our task is to find expressions for v in terms of g, k, and t only. All right. That's our task here. Let's take a look at what are we looking at first. Let's try to visualize that. All right. Now I prepared something for you to visualize here. Okay. Let's look at what happened as the object drop. Okay. Now bear in mind you can observe the length of the vector diagram that represent both the weight and the air resistance in this case. So the weight component remain the same, but as the object fall faster and faster, the air resistance increases. Right. So that's the reason why the length of the air resistance usually is longer as the object drop faster and faster in the medium itself. Okay, so this is what we are looking at. And then bear in mind the motion is downward. It's accelerating downward, of course, in this case. It's accelerating downward. So I'm going to try to put in more parameters here. So it's moving downward with a certain acceleration. And then bear in mind accelerations can be represented using its definition, rate of change in velocity, or we could use the another derivations or accelerations. Okay, so if you derive that, you can actually use dv dx here. Now bear in mind what is x. X is the let's assume that this is where the initial location is located, 0 meter itself, and then since it has already moved x meter here, so the x is the displacement of the particle q in this case after t second. So x is the displacement, v is the instantaneous velocity at that time t. All right, and then a represent the accelerations due to the interactions between gravity and air resistance here. Okay, now first step is always once you understand the visual part, now we have to come back to determine the concept itself. What is the mechanics concept involved? There are not many mechanics concept that is used at the college level or secondary or A level mathematics. Right? Most of the time, it's either Newton's second law, centripetal force, or conservations of momentum or conservations of energy. Now, since we are looking at a linear motion and then there's acceleration involved, so in this case, most probably it reminds us of Newton's second law. So therefore, we're going to use the resultant force is directly proportional to its acceleration. And then, as I mentioned before, we have two versions of the accelerations that you can use, dv dt, or you can use the other one, mv dv dx. Yeah. Okay. Now, which one is more relevant to the questions? Then you have to decide. In this case, you will recognize that we're using t. T represent time. So therefore, we're going to choose the first format, which is dv dt here. All right. So I hope that is clear. Right. Now that is the right hand expression. Now the left hand expression, as I explained before, it must deal with the physical forces that is acting on the particle at that instant of time. So the forces are the weight and the air resistance. So the air resistance is here. Okay, and then its weight. Okay. So therefore, now since the motion is downward, therefore the resultant force must be given by the weight, the difference between the weight and its air resistance. Therefore, this resultant force would produce an acceleration. Okay, so I hope that is clear. Now from here onwards is purely pure math. there's not much mechanics involved. The only mechanics involved is how it actually look like in mid-air, and then how do we relate the calculus algebraic component with the mechanics system. After that, everything's pure. All right. So from here, we get to analyze the pure mathematics algebraically. So in this case, I can simplify that as this. So you can have dv dt here. All right. Now how that's clear. Now you will notice that this is a first order differential equation separable. Therefore, we're going to split them according to their group or their terms in this case. So I can split them in such a way, dt here, right? And then, of course, in order for us to get the velocity expression, we will have to reverse the process of the differentiations. So we'll take that as a integration in this case. I'll perform an antiderivative, so both sides. Okay, so there you have it. All right, now you will have to be familiar with all different types of integrations that you have done so far. Now, for me, I would rather deal with it this way. So I'll take out the k, for instance, in this case. So I'll take out the k this way. Okay, now that would be a dv g over k minus v dt. Okay, that's what we have currently. And then after that, we're going to integrate this. Now that would give us a natural log integrations, which is negative k ln g over k minus v equal to a t uh, plus plus any constant, for instance. Okay. Now from this point onwards here, okay. Now you will notice that if I try to remove the k from the left hand side to the right hand side, you will get a kc and a kt. Now k is a constant, c is also a constant. Therefore, that automatically is a constant itself. So therefore, I can simplify this to this. Now that will be negative kt plus kc. I'm going to label kc using another constant here. Take for instance, I'm going to label that as q, where the q itself is k multiplied with c. Right, so that you are clear what is going on here. And then thereafter, all right, now thereafter, okay, so from here onward, we'll write it down here. Okay, from here onwards, now we can take the anti-natural log in this case. We will end up with g k minus v equal to exponential negative kt multiplied with exponential q here. Now you will notice that exponential q is yet another constant. All right, so you can see that along the way there are so many constants. You can keep on introducing all those constants, or you can actually write as, in this case, you can write as a e negative kt, where the a actually represent e to the power q here. All right, so therefore from here, your v would be equal to gk minus a exponential negative kt here. All right. Now, once you reach this stage, you must come back to the drawing board, seek for or recognize any initial condition or boundary conditions here. Right. So the initial conditions will be here. It starts from rest, meaning that at time t equal to 0 second, its velocity when it was released, it was released from rest. So therefore, at 0 meter per second here. Okay. So from here, all we need to do is substitute this one back into this equation here. Okay, now you will notice that this now that is a 0. Therefore, we can quickly recognize that a must be equal to g over k. And then finally, we can summarize the expressions for velocity as gk. We can factorize that, of course. Okay, and then there you have it. That will be the expressions for the instantaneous velocity of the particle q at any instance time t. All right. Okay. I hope that is clear at this point. All right. I'm going to move on to the next question shortly. All right. Let's look at question 3 now. All right. Now, a particle Q, okay, even though you look at my diagram, I think I accidentally labeled this as particle P, but never mind, it's just a label. So, according to the question, it's particle Q. So, a particle Q of mass m is attached to a fixed point O here by a light inextensible string of length A. Okay, so length A. Now the particle moves in complete vertical circles about O. So it's a vertical circular motion under the influence of gravity. Now the points A and B are on the path of the Q, the circular motion, um, with AB a diameter of the circle. So AB represent the diameter of the circle. Now OA makes an angle 60 degree with the downward vertical through O, and OB makes an angle of 60 degree upward vertical through O. So the speed of the particle Q uh, when it is at A is given as 2 cert AG. Now our task, given that tension A and tension B at the position A and B given there, so we have to find the ratio of their tension itself, right? Okay. Okay, let's take a look at this. Now, as I mentioned before, the first step is to visualize it. Okay, I'm going to show you the visualization. Of course, in the exam, you have to visualize it in your memory then. Okay, let's look at how does it look like. Okay, so it's going to go through a vertical circular motion. I'm going, I think I'm going to show you to go one round there. Okay, let's make it faster here. And then it's going to reach position A there, for instance. All right, now just going to let it run one more time smoothly. And then it's going to stop at position A. At position A, its speed is 2 cert AG then. Okay, so there you have it. So you stop at A. So the speed is cert 2 AG. So the linear speed, we are talking about the linear speed here, is given by cert 2 AG. Right, so I hope that's clear. And then the 60 degree is given as such here, 60 degree. All right. Okay. Now, of course, as it perform a vertical circular motion, it has a certain speed here also that I will label as BB there. Okay, this part is BA here, just to label it so that we can differentiate those two. All right. Now, don't forget, at position A, it has a component, weight component in this case, which is given by it has a mass of m. So therefore, there is mg in this case. All right. And then don't forget, there's a tension here. Okay. And then now I'm going to extend this a bit so that you can see that this is also 60 degree. Okay, this is also 60 degree here. Okay, all right. Now that is what we are getting at this point. So we have a tension at position A, and then we will also have a tension later on when the particle reach this section here. Okay, it has a tension acting towards the center, so we'll label that as TB then. And then at the same time, it does have a weight component also, which is also given by mg there. The motion is towards this direction. All right, so once you recognize the mechanics, okay, and then we know that this is a circular motion, it must involve centripetal force. All right, so centripetal force, that will be mv square over a over the radius itself, or it could be Mr. Omega square. right? Doesn't matter which one you are working on. Okay. All right. Now the first step is to make use of all the informations that we have at this point of time. We know that the speed of the particle Q at position A is given as such here. So we're going to make use of this here. Now we're going to consider Newton. So here I'm going to consider Newton second law at position A here. So at position A, right? Now the resultant force is equal to m v square over A here. Because the radius is given by A here, excuse me, it's given by A here. Okay, and then the resultant force at position A is given by TA. We are analyzing the forces along the string itself. So along the string itself, therefore the resultant force acting towards the center is given by TA. Yes, TA is along this direction. Now, anywhere there's a component mg here, mg is not along the string, so therefore you have to resolve this. In order to resolve that, you will end up with cosine this angle here, which is 60 degree, and then that should yield the m va square, because that's the speed of the particle q at position A there. All right, divided by A there. Okay, so I hope that is clear at this point. Now all we need to do is just substitute all the informations that we have here. So first of all, we can substitute this information. We know that the speed of A at position A there, speed of particle Q at position A is given by 2 cert AG. Okay, so from here, we will have, okay, I think I'll write it down here then. It's m over A. Now the square of this will be 4AG, and then that will be 4mg then. All right, so I hope that's clear. From here, we can deduce that the tension of the string at position A is given by 4mg, sum up with mg cosine 60 there. If you press the calculator, cosine 60 is a half. So therefore, the total tension here is 4.5 mg. All right. So we have obtained the tension of the string at position A given by 4.5 mg there. So I hope that's clear. Now next, we are going to obtain the tension for the string at position B, just like what we did just now, right? Now don't forget this angle also is 60 degree. Okay. Now we're going to consider same thing. So here we're going to consider forces um, along the string at position B now. Right. At position B now. Right. Now applying the Newton's second law would yield TB plus mg cosine 60. This will be the resultant force in this case. You can see that both of these forces are actually acting towards the center itself. So therefore the resultant will be this, will be equal to m bb, the speed of the object at position B here, divided by A there. Okay, now at this point, all we can write is, okay, now TB is the same as mvb square over A minus of cosine 60 is a half, as I mentioned before, so 0.5 mg. Now, what's left next will be the to find out what is the speed of the particle at position B. Right. So we can leave it here, equation number 2. Okay, now in order to obtain the speed of the particle Q at position B, we have to make use of the conservations of energy here. Okay, now before you do any analysis using conservations of energy, um, personally I find that it's easier if we draw a reference ground, I would say, or a reference line for us to use our conservations of energy in this case. Right? Okay, so by using conservation of energy, here I just write it down in short. Okay, no, that in short also is wrong. Okay, COE. All right, so conservation of energy. Now the total energy at position A must be the same as total energy at position B here. Now at position A, the only energy involved, since we use this as a reference, the only energy involved is kinetic energy, which is half mv squared. Okay, since we put our reference ground here, there is no gravitational potential energy with reference to the ground that we have set up here. This is not actually the physical ground, this is just a mathematical ground. Okay, now that should produce the same amount of energy at position B. At position B, it has both the kinetic energy and gravitational potential energy. So the gravitational potential energy is given by the height. So we are talking about the height from here down to the vertical ground here. So that height can be given by using a bit of trigonometry, because this is 90 degree here. So therefore you can take 2a uh, 2a cosine 60. Okay, and then there you have it. From here, we can simplify along the way. So if I simplify, I will get a BA square, the same as BB square, and then plus of because I removed the 2 already, so here I will have the M can be removed, so 4 A 4AG, yes, correct. And then cosine 60 is a half. Now that's what I have. And then if I try to simplify, and then knowing that the speed of particle Q at position A is given by this, so therefore I can also write this one down here, this speed here, as given as 4AG after we square. Right. Now from here, we will be able to conclude the speed of B, the speed of particle at position B there, right? So which is actually 2ag here. All right. Now we can use the square of the speed at position B there, because from equations number 2 here, all we need to do is just use the square of the speed. We don't really need to square root this, right? Okay, and then there you have it. This is what we have, and then of course here I'm going to make a highlight. Okay, now you'll notice that all we need to do is just substitute this one back here. Right, so if you substitute this one back here, right, you will get 2 mg. So 2 mg minus of this, therefore the tension of the string at position B would be 1.5 mg then. Okay, and then finally we are interested to find the ratio between TA, tension at position A, and tension at position B. Now that will be given by the tension here, 4.5 mg to 1.5 mg there. Alright, now it's very obvious that is actually 3 to 1 ratio. Alright, so I hope that is clear for this question here. Right, now I'm going to move on to the next question shortly. Alright, question number 4 is a problem about center of mass of a rigid body. A uniform solid circular cone. Okay, you can see it from the diagram here. of vertical height 4r and a radius 2r. Okay, is attached to a uniform solid cylinder. So the cylinder is below the cone itself. The cylinder has a height of 3r, and a radius of kr, where k is a constant less than 2. Now the base of the cone is joined to one of the circular faces of the cylinder, so that the axis of symmetry of the two solids coincide. You can see it from the diagram itself. Now the cone and the cylinder are made of the same material. Same material meaning that they should have the same mass density. Okay, all right. Now from here, we need to make a few remarks first before we start to work this out. Now, first of all, since the material are made up, both the rigid body are made up of same material, therefore they should have the same density. Okay. Now next, the mass. The mass of the rigid body or the solid itself is given by density multiplied by the volume itself. Therefore, you can say that the mass is directly proportional to the volume itself. Now, since the mass is directly proportional to the volume, if you don't have any information regarding the mass itself, we can replace it with a volume itself, right? Okay. Now, if you don't want, you can actually include the density, which is not very important in our analysis here, right? Okay. Now, the first step. Any center of mass question is best to set up a form of table in this case. Right? So the form of table that we need will be something like this. We will have to have uh, the the volume of the cone, and then the components that we are looking at. So we must have um, the mass itself. So we must have the mass of the solid. First of all, we have both the cone, and then we have the cylinder, and then don't forget, both of these joined together will give us the combined, combined solid. Okay. Now, don't not forgetting, we must also get the center of mass in this case. Okay, so um, center of mass. So where is the mass located? Now, since this rigid body is symmetrical about this axis here, therefore the center of mass must be located along this line of symmetry here. Okay, so therefore we don't really need to consider the other component um, other than the distance from the vertex itself. So we are interested to find out where is the center of mass measured from the vertex itself. So this is the vertex. All right. So we are ready at this point. Okay. All we need to do is write down all the informations that we need here. Yeah. Now, first of all, the mass for the cone. The mass for the cone is uh, 1/3. Okay. 1/3 1/3 pi r square. Now the radius for the cone is 2r, so therefore 1/3 pi r square. Sorry, I missed out my pi there. Okay, so 1/3 pi r square. So that would be a pi. Okay, so in this case we have 4r square here. So 1/3 pi r square multiplied by the height itself. So that will be 4r. Now this is the volume of the cone. And then we know that the mass of the cone is given by multiplied by its density itself. Okay, I hope that's clear. Now next for cylinder. For cylinder is much more easier. It's just pi. Okay, I'm going to use a different. It's a pi r square h. So pi r square h, the radius of the cylinder, which is kr, pi r square multiplied by the height of the cylinder, which is 3r in this case. Okay, and then there you have it. There's a volume for the cylinder, and then of course you need to get the mass. We have to multiply by the density. So the combinations of the mass would be easier in this case. You can of course factorize this. Okay, now take for instance in our case that should be 16 over 3. Okay, let me see, 16 over 3. Yep, correct. So plus the 3k square. Right, now the rest are pretty much the common factor in this case. You will see that is pi r cube density. Right, I hope that is clear. Now center of mass. Center of mass measured from the vertex itself is along the line of symmetry. Okay, now let's start from the cone itself. Okay, now if you're not sure where is the center of mass of a cone, you can always refer to the data booklet. Right, here it is, the data booklet, MF19. If you can't recall what is the where is the center of mass for a solid cone or a cylinder and so on, it can be found in this data booklet. Now look under this section here, solid cone or pyramid of height h. Now the center of mass measured from the vertex is three quarter of the height of the cone itself. So that three-quarter is basically just 3r. So it's located at 3r here. Right? Now I hope that's clear. Okay. Now once you're ready, we're going to write this one down now. So the center of mass is basically just three-quarter. So I'm going to write down three-quarter the height of the cone itself. So the cone is 4r. Now that will yield 3r there. Right. Now next, we have a cylinder. A cylinder is quite easy because it's uniform. Now cylinder is the center of mass must be at the center of the height here, which is 1.5. But since we are measuring the center of mass with respect to the vertex itself, and then therefore we must add the 4r here. So 4r plus 1.5, you get 5.5. Okay, now here I just write down 4r plus 1.5r, which will yield a 5.5r here. Okay, now I hope that's clear. And then finally, the combined center of mass, which we don't know. If we label the distance from the vertex as y, so I would assume in this case it might be somewhere here or somewhere here, for instance. So let's assume that it's somewhere here. Then I will just label the distance measured from vertex to the center of mass, maybe here or at the top. I'll use this symbol, y bar here. Okay. All right. Now I hope that is clear. Once you are ready with this, okay, we can go through the analysis by using principle of moment. The combined moment must be the same as the sum of the individual moments that that we can obtain from each individual rigid body. Okay. Using that principle of moment, we can write down 16 3 plus 3k square multiplied by this. This is the moment. Must be the same as the sum of each individual moment. Now that would be this one here. That is typically, let me see here. We have 16, so just left with 16. Okay, 16 pi r4 now because it's cube here. Okay, and then you have the density, and then after that here you have like 16.5 k square pi r4 density. This is 234 k square. Yep, correct, right? Now, of course, we can remove all the common factor here because they are non-zero constant. So like pi, we can remove it. The R4, we can remove it according to R3. And then the density is uniform, so we can cancel out that. Therefore, we can simplify the expression so that it looks something like this now. Okay, so that will be 16 r plus 16.5 k square, k square r actually. Okay, so maybe um, I would just factorize this, then it'll be easier. So I just write down 16 plus, and then there's the r then. Okay, and there you have it. And then of course we can get rid of this 3. So if we get rid of this 3, you will get a 9k square y square here, 48. Uh, so 49.5 k square. Right, now if you want to turn everything to an integer number instead of a decimal, you can multiply 2. Okay, so that will be 32 18k square, and then that will be 96, and then this one will be 99k square r. Therefore, the center of mass for the combined rigid body is given by 96 over 32 plus 18k square. Now don't forget there's a r there. Let me check whether that is correct. 96 by 99k square, 32 by 18. Alright, now there you have it. We managed to prove that the center of mass for the combined rigid body is given as such. Alright, now I'm going to move on to the section B for this question shortly. Alright, for the section B of question 4, the point C is on the circumference of the base of the cone. Alright, now you can see that from the diagram there. Now when the combined solid is freely suspended from C and hanging in equilibrium, now the diameter through C makes an angle alpha with the downward vertical, where the tangent alpha is equal to 1 over 8. Right. Now given that the center of mass of the combined solid center of mass of the combined solid is within the cylinder, find the value of K here. Right, now I would like to show you the 3D model, how the object actually look like. Okay, now I'm going to, yeah, okay, walk this through. Okay, let me see. Okay, now you can see that I'm going to show you the three-dimensional perspective of this object. If you can't visualize it, so the diameter is CD there. The C is on the circumference of the base of the cone. Now, okay. So once you hang the combined solid, okay, at C, now the line, the vertical line that passes through C, must pass through the center of the mass there. Must pass through the center of the mass. That would usually be the case because this is the point where all the weight is assumed to be acting. So this is where the center of mass is actually located. We know that the distance from here itself, okay, from here, okay, up to here. All right. Now, bear in mind, in this case, I'm just making assumptions that it could be somewhere here. Then again, the center of mass could be here also. If you want to be much more clearer as to whether it's here or here, you can always check out the algebra of that. Okay, and then to see whether it will be here or here in this case. All right. Okay, we can do a little bit of testing shortly later, right? But let's assume that it's somewhere here first, and then what they mention about the alpha is actually this angle here. Okay, so the alpha is actually there, and then we know that the length here is 2r, measured from here. Okay, and then this is 4R here, measured from here to here. So therefore we need this height here, so we need this length here, for instance. So that length can be obtained by using y bar minus of 4r, then we should be able to get this. Therefore, in this case, okay, we know that tangent alpha can be given by, based on this geometry, can be given by L over 2r, which is the same as 1 over 8 in this case. Okay, now knowing that L is actually given by the y var minus 4r there. So from here we can write down, now previously we have already found the y bar, so I'm going to write down the y bar again. Not sure whether I still remember. I'm going to refer to the answer one more time. So we have 99, I think it's 99k square plus 96 here over 18k square plus 32 r there. Let me check whether that's correct. Okay, that is correct. Right. So from here, all you need to do is just obtain our L here. So I'm going to work out my L first. Now that would be 99k square plus 96 here, 18k square plus 32 r minus of 4r. Alright, so from here I should be able to obtain, let me see, 72, so that will be 27k square, and then this one will be, let me see, what do I have here, 128, so 128, that will be 32. Okay, so that will be 32 over 18k square plus 32. All right. Okay, now that will be our R. So now we are ready to make use of this result here. Now that will be typically, um, now let me try to simplify this. So you can actually put L on top and then divided by 2R. The R can be cancelled out, and then therefore I can, after simplifying, so after I simplify that, I would be able to get k square minus 32 over 18k square plus 32 would be equal to a quarter. Then if I bring my 2 over there, it will be easier for me to calculate here. Now you will notice that this one will be 108k square, okay, 128 equal to 18k square plus 32 there. And then therefore in this case you have 90k square, and then now we have 160 there. Therefore, now in this case, k is actually equal to plus or minus 4 over 3. But we do not notice that k is greater than 0. It's the length itself. Therefore, we conclude that our k is equal to 4 over 3 because it must be greater than 0, but we know that the k must be less than. We also given that. Let me finalize this. So k is equal to 4 over 3 because k must be greater than 0 but less than 2 according to the statement here, right? So I hope that is clear. That's how we obtain the value of k using all the result that we have obtained by far. Okay, right. Now, as I mentioned before, we're going to do a bit of experimentation as to see whether the center of mass is actually located somewhere here at the cylinder sections, or is it before here? Okay, so the test is very simple. Let me clean this up here, and then we're going to look at how we are going to test this out. Okay, so identify. So the key thing here is to identify the proximate center of mass. Okay, the approximate center of mass. So at least we know whether it's here or whether it's here. Okay, now we know that the one that we have obtained is y bar equal to, okay, 99k square plus 96 here divided by 18k square. Is it 18k square? Yeah, correct. 32 r. Okay, all right. So let's make one assumptions there. Okay, let's assume that it's over here. So therefore, we can actually take the difference between this with a 4r there. We have already obtained this previously. Okay, so that actually gives us 27k square minus 32 over 18k square plus 32 there. Now we also know that the k must be greater than 0 and then less than a 2 here. So this is the remark here. So the k, all right, now let me write it down properly. So the k are all real number such that the k is greater than 0, less than a 2 here. Okay, so it's less than a 2. Now, if we put a 0 here, okay, it can't be 0, of course, right? Now, if you put a 1 here, if the k is 1, yes, it's possible that the center of mass would be somewhere here. So it's possible that the center of mass could be somewhere here. So if the k is around 1.5, for instance, okay. So here, if I make an assumption, so if we assume y minus 4r is greater than, okay, if greater than 0 here, so therefore we notice that the denominator must be 0, therefore 27k square minus 32 must be greater than 0, k square must be greater than 32 over 27 there. All right, k square must be greater than this. And then if you use your calculator, okay, just let me try to gauge what would be the value for k in this case. Okay, let me try here. So that is actually 32 divided by 27. Okay, and then I'm going to square root that, 1.19 approximately. All right, so this value here most probably will be k would be greater than approximately 1.09 here. So the k will be greater than 1.09, and then of course less than 2 then. Okay, so it's possible that the center of mass could be somewhere here. Right. So therefore, I did not actually conclude that the center of mass could be somewhere here. That is just my initial assumption. So let's assume that in the exam, if you are not sure, if you assume that the center of mass is somewhere here, therefore, the angle made by this line that passes through the center of mass would still be alpha here. Would still be alpha. And then all you need to do is we still need to check the difference between this. So therefore, the way we did it will be the difference between this one here. We will have to take the magnitude of the difference here divided by the radius of the cone itself, which is 2r, and then that would actually yield the tangent alpha, which is equal to 1 over 8 here. Okay, so in this case, you can actually give it a try. Okay, give it a try. For instance, like previously, I did not use a modulus sign here. So in this case, if we try to use modulus sign, therefore, it is possible that we could actually end up with 32 minus 27k square over 18k square plus 32 equal to 1 over 4 here. And then solving this, okay, let me give you a try here. If I try to solve it, I will get like, okay, I'm going to write it down here, this side here. So I have 128 minus 108k square equal to 18k square plus 32 here. And then from here, I will get my 126, yeah, 126k square, and then that will be 96 then. Is it 96? Yep, correct, 96. Therefore, the k would be, okay, so the k would be 96 over 126 square root of this. Okay, now let just give it a try here. So that will be a 96 divided by 126. Okay, hold on. I think it's easier if I put down here 96 divided by, okay, hold on. I think it's better if I put here 96 divided by 126. Alright, so therefore the k that I will get in this case will be 0.87, 0.87 there, right? So therefore in this case it's possible that the value of k could be 0.87 if the center of mass is somewhere here, right? Now that would clear your confusion as to how do we know that whether the center of mass is somewhere there or on top there, right? All right. Now, just before I miss this out, okay. Now I need to clarify one thing before we go with this question here. Even though we have two values of k here, but due to the facts that the question mentioned the center of mass is located in the cylinder section, that's the reason why we make assumptions to choose our center of mass right here, not here. But in the exam, if they don't actually give us any clue as to where the center of mass is, then therefore it's possible that we can have two values of k there in case they change your question, right? So I hope that will be an extra information for you, right? All right, question 5 is relating to collision of two rigid bodies, or sometimes we call that oblique collision, right? Now we have two uniform smooth spheres A and B with an equal radius. Each have a mass m. The two spheres are each moving with speed u on a horizontal surface when they collide. Immediately before collision, A directions of motion make an angle alpha with the line of centers, and then whereas B directions of motion is perpendicular to that of A. Okay, now see the diagram. I'm going to show you the diagram in a while. Now the coefficient of restitutions between the spheres is given as E, a constant there. Immediately after collisions, B move in the directions at right angles to the line of center. Okay, let's try to visualize that before we start proving the first statement. Okay, now this is how it actually look like. So A and B will move and then collide. Okay, now the directions of A before the collision is making an angle alpha to the horizontal line that passes through their center of mass in this case. Okay, you can see that quite clearly. Okay, so this is A in this case. So this is A. This is B here. Right, now each one of them is moving at a speed or at a velocity u here initially, and then they sort of collide. Okay, all right, now that's how it actually look like. Let's look at, so don't forget after the collisions, B actually move vertically upward, so vertically upward in this case. Let me see whether I have that diagram with me or not. Okay, let me see. Okay, show you one more time. So they collide. All right, now that's how they look like. So after the collisions, this B would move in the direction at right angle to the line of center. So what they mean is this B would actually move in this direction. Okay, vertically upward. All right, so I hope that is clear at this point. Okay. So from here, we're going to prove that the tangent alpha is actually equal to this. Right. Now there are two concepts involved when it comes to collision, oblique collision in this case. The first one is Newton restitution's law, and then secondly, we have to apply the conservation of momentum. All right. Okay. Now let's consider the horizontal component of the collision. So the horizontal component of the collision. Uh, let's consider horizontal um, impact or impulse here. Okay. Right. So from here, we can actually apply the Newton restitution's law. Okay. Now bear in mind, for object B, sphere B, there is no horizontal component. There's no horizontal component after the impact. So anyway, the vertical component here, all right, now that does not look very straight. Let me correct that. Okay, so this one's supposed to be vertical. Now the vertical component of the velocity after the collision must be the same as u. So in this case, it must be a u sine. So u sine 90 minus alpha is actually u cos alpha because we assume that the surface is smooth. Therefore, there is no impact um, along the tangential surface between the two spheres here. And then the same go for A also. So A, after the collision, the vertical component of its velocity is also given as, in this case, is u sine alpha there. All right. So I hope that is clear. Now its initial velocity, okay, its initial velocity is given here. That is actually u cosine alpha. Let's assume that this direction is treated as positive. That's very important. And then as for B, its initial velocity is negative directions to this. So that is actually negative. U cos become u sine alpha there. All right. So I hope that is clear at this point. Okay. All right. Now we are ready to apply Newton restitution's law. By applying Newton restitution's law, okay, we can say that. All right. Now let's assume that after the collisions, there is a vertical component for the sphere A. So let the vertical component for sphere A be B A y, and then B A x. So let the um, let the component um, velocity of A after collision be A. Oops, A. I shouldn't call it A. Let that be BAX and BAY. So the AX is in the horizontal component, AY is in the vertical component. Now, whereby in this case we have already found the AY. This is the vertical component of sphere A after collision. Right? But we have no idea what is its horizontal component here. Okay. And then the same go for B. Now the vertical component of B is given by this. Okay, hold on. So that is given by this one here. This is B, B, Y. Okay, whereby the B, B, X, the horizontal component of the sphere B after collision is actually equal to 0 because it's moving vertically upward. Okay, now first of all, let's try to apply conservations of momentum first. So COM, conservation of momentum, and then by taking into account its horizontal component during the collisions itself. Okay, because the impact or the impulse is only important when you deal with the um, direct contact along the line that passes through their center of mass, not tangent to that. Right? So let's apply conservation of momentum along this direction here. Therefore, um, we have total momentum before collision and after collision must remain the same, provided there is no external force acting on the system here. So therefore, I will have mu cosine alpha. Okay, mu cosine alpha. The initial one will be here. Mu sine alpha. Okay, must be the same as. Um, okay, so m b x plus mvax here. So all the x component, right? Okay, right. Now from here we know that the horizontal component after the collisions for sphere B is equal to 0. Therefore, we can simplify this as the horizontal component for sphere A after collisions will be given as the cos alpha minus sine alpha u. Okay, now there you have it. That's a very important result that we're going to make use in a while. Now next, by using Newton restitution's law. So Newton restitution's law, I just write it down in short. Okay, now it says that the relative speed of separation uh, divided by relative speed of approach must be the same as the restitution's constant, coefficient of restitutions here. Right? So let's do the separation. So therefore, we are looking at the horizontal component again because the impulse is only available for um, impact along the horizontal line here. So therefore, that will be, now let's try here. We can try BBX minus BAX here must be the same as the initial here, U cos X, subtract off with the, because the direction is negative, so therefore there is U sine alpha must be the same as E here. And then we know that BBX is equal to 0. And then therefore, in this case, let me see whether I got it correct. So this is minus B, 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 BBX minus this is equal to this one here. All right, okay. Let me check if I got it correctly. Hold on, let me check for. All right, so after checking everything is correct, so all we need to do is just simplify this. Okay, now you can see that from equation number 1, we can actually rewrite this as sine alpha minus cos alpha. Right, now the u will be cancelled off. Once I substitute number 1 into number 2, all the u will be cancelled out. All I have is just sine alpha plus cos alpha here equal to an e there. And then of course I can divide my numerator and denominator by cosine I will have a tangent alpha minus 1. That is tangent alpha plus 1 equal to an E there. And then of course, I can do a bit of algebraic manipulation here. I will have E tangent alpha plus E is equal to tangent alpha minus 1. Okay. Now from here I will get E minus 1 tangent alpha is equal to 1, or E plus 1. Is it E plus 1? E plus 1. Oops, I think I sent it over to the wrong directions here. Just let me change that one more time. That should be 1 plus E here. Okay, 1 plus E here, and then there is 1 minus E. And then therefore, our tangent alpha is the same as, right, is that the same? Yep, correct. Right, therefore it is proven here. Right, now I hope that is clear for this question. We're going to move on to the next sections of question 5. All right, second part of question 5. Immediately after the collision, B move in a direction at right angles to the line of the centers. Now, given that tangent alpha is equal to 2, find the speed of A after the collision. Okay, now let me show you what we expect to see again. Okay, all right, now first of all, they collide, and then after that, B move in the vertical direction. Okay, now I'm going to rewrite again all the informations that we have previously. So first of all, we have U is here. Its original initial velocity is U cosine alpha. Now this one is making a reference in this direction as a positive. So this is also U. So that is U sine alpha. All right. Now we know that B is moving in this direction. So therefore, By is actually given by U cosine alpha there. Okay. Knowing that BBX is actually equal to 0 because there is no horizontal component for motions of B. Okay, so that is it. Okay, hold on, just let me touch up my writing here. Okay, that is in the X component there, right? Whereas for A, okay, now it has both the horizontal and the vertical component. So let me write it down here. Hold on. That's not very straight. Okay. So the vertical component of A after the collision is actually given by U sine alpha. Alright. Now, whereas the horizontal component of A after the collisions, we are going to figure that out now. Okay, now given that tangent alpha is equal to 2, we can use a simple triangle here. Okay, so just let me draw a right angled triangle here. Okay, now just with reference to alpha here. Okay, now since tangent and then the alpha is an acute angle. So since alpha is an acute angle greater than 0 degrees Celsius, less than 90 degrees Celsius, so we can assume that this would be given by 2, 1 here, and then this is cert 5 here. Okay, knowing this, we can actually figure out that the cosine alpha is actually equal to 1 over cert 5, whereas the sine alpha is equal to 2 over cert 5, right from this right angled triangle. Right? And then from the previous sections, we have actually found out Vx here is typically cosine alpha minus sine alpha U. So therefore, we're going to substitute this one in. Now that will be cos, and then a sine is this. u. Okay, right. So from here you found that this is actually negative, uh, negative, yeah, correct, negative u over cert phi. Okay, so this is just my assumption. Since it's negative, all right, let's assume that going up is considered as positive, going to the right is considered as positive. Therefore, the actual motions of A is actually moving this direction, not upward. Okay. Hold on, is that correct? Oops, sorry, my bad. This is the horizontal component of the motion, not the vertical. The vertical is still remain the same, but the horizontal, yes, is moving towards the left hand side. So it's going to move this direction instead. So the B A X, I'm going to write it down here. So B A X is in this direction. Okay. There you have it. So most probably it's going to move in this direction. Now that will be the speed of A after collisions there. Right. Now we knew the vertical component of the velocity after collisions for A is given by u sine alpha, and then we know the sine is this, so therefore there is 2u sub phi. So the speed of A after collision. So after collisions, BA here, will be given by the theorem Pythagoras of the x and y component. Okay, now that would typically be 1 over 5 plus 4 over 5 there, square root u in this case. And then let me check whether I got it correct. 4 and 1. Okay, therefore the speed of A after collision is just equal to u, meter per second in this case, right? Okay, if you want to know the direction, for instance, just for the extra um, analysis in this case, since this is BAX here, so therefore the directions of the motions will be somewhere here. So that will be the directions of the motion. Now you can actually relate that angle after the collision. So take for instance in this case the directions of the motion making an angle theta to the horizontal to the left in this case, right? So therefore the angle can be found by using its u sine alpha over the what do we have for the for this? Okay, for VAX, VAX is equal to this, which is now we are only interested in the magnitude itself. So here I just take the magnitude, sub 5. Okay, and then the u cancel out. We have sub 5, and then sine alpha. Sine alpha is actually 2 sub 5 here. So therefore, you found that tangent is actually equal to 2, which is exactly the same as the original angle before the collisions there. Now, of course, you can use your calculator to estimate the angle here, right? So this one I will leave it to you with your calculator, right? So I hope this collisions question is clear. I'm going to move on to the next questions shortly. All right, question number 6. All right, it's a projectile motions question. A particle P is projected with speed u. Okay, we can see that this is speed u here. Okay, at an angle theta above the horizontal from a point O on the horizontal plane and moves freely under gravity. You can see that from the diagram itself. The direction of motion of P makes an angle alpha above the horizontal when P first reaches 3/4 of its greatest height. Now we need to show that the tangent alpha is equal to half a tangent theta there. Now let me show it to you what they are talking about here, right? Now let me show you a little bit of animations here. Now this particle P is being launched. Okay, you can see that here. Okay, I'm gonna launch it now. Is it moving? Okay, now it's launching. Okay, it's moving now. All right, now it should reach the ground normally. All right, now let me show you one more time. It will launch and then reach 3/4 of its greatest height, for instance. For instance, is somewhere there. All right. Therefore, it make an angle alpha to the horizontal. Now, that is what the questions is referring to, the theta and alpha itself. Okay. All right. Okay. Now let's try to go through all the properties for this projectile motion before we try to solve it. Now there are many ways you can actually solve it here, but personally I prefer to use the divide and conquer strategy rather than using the combined formula that you can found in MF19 there. Okay, so based on my personal preference here, I would prefer to label first of all, because it moves at speed u here. So therefore, I would usually resolve its horizontal component and vertical component. So its horizontal component is given by this. Its vertical component is given by u sine theta there, right? So I hope that's clear. Now the same goes for this. When you reach 3/4 of its greatest height, okay, if the speed is v, therefore this one will be v cosine alpha. Okay, this is the x component, and then its y component will be the same as v sine alpha here. Now we know that by ignoring air resistance, therefore the horizontal component throughout the trajectory, right, will not change. So therefore, its horizontal component of the velocity remain the same as its horizontal component of the projectile motions, okay, before it was launched. Therefore, due to ignoring air resistance, we can conclude that the horizontal component remain the same as its initial component, which is the same as this one here. All right, now I hope that's clear. Now the only component that will change is the vertical component of the velocity. All right. Now let's take a look at how to work with this. Okay, now first of all, we may be interested to find out what is the greatest height. Okay, so since they talk about the greatest height, now the greatest height would be somewhere here. I'll just label the greatest height as h then. It'll be easier to refer. So in order to get the greatest height, we can make use of some of the suvet here. So I'm going to write down some of the suvet. The suvet that we are going to use is this one here. Okay, now bear in mind, okay, we have this suvet here, or we could use this one, okay, or we could actually use this one here. So these are the three general suvet equations that personally I always use. Of course, there's another one that is given by the data booklet, which is derivations from three of this, right? So for this example, I'm going to use the first suvet equations here to find the maximum height. Okay, my intention is to find the maximum height. Now, of course, in the exam, it's better to write down the y component because we are interested to uh, evaluate its maximum vertical component of the height. So therefore, this equation here, every component of the velocity and acceleration must refer to the vertical component of their quantity. So this vertical component, this one must also be a vertical component. A must also be vertical component, and then this one will yield the maximum height. All right, now a remark here, the vertical component of the acceleration is basically the same as negative 10 meter per second, using the approximation given in the paper itself. Okay, all right, so from here, we know that when we reach the maximum height, its vertical component of the velocity must be equal to 0. Okay, So therefore, in this case, we'll have 0 here. The initial vertical is given by u sine theta minus 2gh. Therefore, we will be able to discover the maximum height in this case, which is equal to this. Okay, so there you have it. That is the maximum height. Now, 3/4 of this maximum height is somewhere here. So this is like 3/4 of the height itself, of the maximum height. Okay, 3/4 of that, right? Okay, as I mentioned before, the vertical component never change. By using the same Suvet equations again, right? But this time we are going to use this new height here. Okay, h1 for instance. Okay, now using the same Suvet equations, we know that at this instant of time, its vertical component is this. So therefore in this case, using the same one, I can write down v sine alpha square is equal to so its initial is u sine theta square minus 2g h1. Okay, and we know that h1 is basically given by 3/4 of that, right? So from here, we will be able to get sine square alpha equal to u square sine square theta minus 2g. All right, now the h1 is 3/4, so 3/4 of the height, which means is this height here. 2g. Okay, this part here is here. Okay, so there you have it. And then we're going to simplify our right hand expression here. Let me see what do we have here. The 2 cancel, so you have 3/4, and then you have 1/4 u square sine square theta. And then by taking the square root, we will have sine alpha equal to 2u sine theta here. Now bear in mind here, we are only interested in the positive value because it is above the ground itself. So all the value, the angle, and then the speed itself, they are all positive values. So therefore, I did not include the analysis related to negative here, right? And then from here itself, okay. So we can try to simplify this, right? Let me see what do we have here. Okay, that is actually a v sine square. Okay, hold on, let me see here. Okay, the sign that we have here. All right, now there you have it. That's our sort of our first equation. And then bear in mind we also have the second equation here. We know that the second equation state that the Vx is the same as Ux. So the vertical component, the horizontal component, which is V cos alpha, is the same as U cos theta there. Now that will be our second equation. By solving both of these, taking 1 divided by 2, for instance, we will be able to obtain tangent alpha equal to half tangent theta there. Is that correct? Okay, good. All right. Now that proves the first statement given there. All right. I hope that is clear. I'm going to move on to the questions B shortly. All right, we are back. Let's look at the second part of this question 6. All right. Now, given that tangent theta is equal to 4/3 now, okay. Now we need to find the horizontal distance traveled by P when it first reaches 3/4 of its greatest height. I'll give you answer in terms of U and G. All right. Now I think I still have the simulations here just to show it to you again. Okay. So it will travel. Okay, that will reach the ground, of course. All right, now I think I'm going to show you the position where it ended in mid-air, making an angle alpha there. All right, and now what we are interested to obtain is here. We are interested to obtain its horizontal distance traveled by p. So that is typically here. Let me mark it down here. The horizontal displacement. So here I just label as x. It's easier to relate here. Okay, so that's the horizontal distance traveled by p. Okay, this is the vertical distance traveled by p at this instant of time. Okay, all right. And then we have obtained one relationship between the uh, theta and the alpha itself. All right, now we know that tangent alpha is equal to half tangent theta. Is it correct? Yep, correct. All right. Now we are given that tangent theta is equal to 4 over 3. So therefore, that will be 4 over 3 there. That will give us 2 over 3. So tangent alpha is actually equal to um, 2 over 3. Okay, so that's our tangent alpha there. Now, in order to obtain the horizontal distance, so the horizontal distance again, we're going to refer to our Suvet equations here. All right, so these are the two Suvet that we are going to make use of to solve this horizontal distance, right? So we're going to make use of these two Suvet equations here. Okay, now other than that, this is what we have obtained previously. We know that u cos is equal to v cosine here. This is what we have obtained previously. And then we have also obtained previously regarding the 3/4 height here. So I'm going to rewrite that one more time. So we make use of these Suvet equations just now to obtain the vertical component of the velocity at this instant of time. Okay, so now this is actually given by v sine alpha, and then this is given by u sine theta square minus 2g, and then the y is 3/4. Okay, so that is typically 3u square sine square over 8g. Okay, so you can see that from here we have indirectly obtained 1/4 of u square sine square theta, and then we have simplified that in our previous section to be 1 over 2 u sine theta here. Okay, so now we are ready. This one will be our second equations. We'll see whether we are going to make use of those. Okay, we're going to start off by using this one here, these two equations. Now Vy equal to Uy plus Ayt here. Now bear in mind our A is our vertical component, which is the same as negative g. Okay, now we know that the vertical component is given by v sine alpha, which is the same as sine theta here minus a g t. Now the purpose of this is to find out how long does it take to reach 3/4 of the height here. Okay, now we know that v sine is actually given by this half u. Okay, you can see that there's a half u sine. So half u sine theta is equal to u sine theta here, gt. So from here, we should be able to figure out the time. How long does it take to reach the 3/4 height here? So that is simply half a u. So half a u g sine theta. Okay. And then we know that sine theta is actually 4 over 5. Therefore, we can simplify that as 4 over 5, so that will be a 2u. Okay, you can see that 2u, and then 5g then. Okay, 2u 5g. So that's the time. Knowing that the time taken to reach that 3/4 height, therefore we can conclude that the horizontal displacement at that instant of time is actually given by its horizontal um, velocity, which is u cos theta multiplied by t here, which is also from this Soviet equation, right? So that will be the same as u cos. So our cos is 3 over 5 u, and then the time taken is 2u over 5g. And then therefore, let me see what do we have here. We have 6u square over 25 g. So the time taken to reach that 3/4 height is given here, and then therefore we managed to find out the horizontal distance traveled by p when it first reaches 3/4 of its greatest height. All right, so I hope this has been useful exposure to you. I'm going to move on to the last question shortly. All right, our last questions today, section A. This is a spring mass system. So now one end of a light spring of natural length A and modulus of elasticity of 4 mg is attached to a fixed point O there, according to the diagram. Now the other end of the spring is attached to a particle A having a mass km, where k is a constant. Initially, the spring lies at rest on a smooth horizontal surface and has a length A. Now, a second particle B of a mass m is moving towards A with a speed 4 over 3 GA along the line of the spring from the opposite directions to O, as shown in the diagram also. Now, particle A and B collide and coalesce, meaning that they join together as one body. Now, at a point C in the subsequent motion, the length of the spring is 3 over 4a, which means it has compressed 1/4 of the original length. And the speed of the combined particle is half of its initial speed. Okay, now let me show you how does it look like. How does it work? Let's look at visualize the mechanics first. Okay, you can see that B move towards A, they coalesce, and then after that the whole body will move, will compress the spring. Okay, will compress it quarter A. Okay, now that's how it look like. Okay, now we're going to do it with two stages here. So the first stage is we're going to analyze the collision between A and B first. Okay, so for the collision itself, I'm going to start from here. Okay, since there's a collision involved, you must remember to use conservations of momentum. So here I'm going to use conservation of momentum. Okay, so in this case, using conservation of momentum, we will have let's use a simple symbol to represent the initial velocity of B in this case. All right, so that is the initial velocity of B that is moving towards A there. Okay, so just let me show you one more time here. Okay, now this is how it looked like initially. So therefore B is moving towards A with this speed. Okay, with this speed. Initially A is at rest. Okay, 0. All right. So by using conservations of momentum, yeah, by the way, this is Km, this is M. We can obtain this one here. All right, must be equal to, because they collide and coalesce, so therefore they will join as one body here, and then move with this particular speed there. Okay, right. Okay, so from here, we will be able to deduce the speed just before it start to compress the spring when they collide and coalesce. So therefore, B is equal to um, 1 plus K here. All right. Now that is the speed just before it start to compress the spring here. All right. So let me show it to you. How does it look like here? So basically it looks something like this. You can see a coalesce. Okay. This is the speed just before it compresses the spring. So therefore it's moving at V here. Okay. All right. Now at a point C in the subsequent motion, the length of the spring is 3/4 A now, and the speed of the combined particle is half of its initial speed. Now, this initial speed is a bit confusing. The initial speed that they are talking about is this. So when you reach position C here, now let me try to see whether it works or not here. You can see it compresses, okay, up to here. So once it compresses up to here, now the length become 3/4 A, and then the speed here become half of its initial. That's what they actually mean by that, right? So I hope that you are clear with that. Now, after it coalesces and then compress the spring, we can use conservation of energy in this case. Okay, conservation of energy. We know that it has an initial kinetic energy, which is, oops, this is the one part that you have to be very mindful here, okay, because it consists of two body now, which is 1 plus km now. Okay, so it has an initial speed of v square. Okay, and then this energy will be converted to kinetic energy also, which is, all right, and then when you reach half of its initial speed, so half of its initial speed. So I just like to clarify this initial speed. They are referring to just before it start to compress the spring. And of course, the spring would gain um, elastic potential energy. So the elastic potential energy is given by 4 mg over 2a here. And then the compression. So the compression is 1/4 a squared there, right? So that's how it look like. Okay, so from here we can simplify these two terms here. This is 1/4 v square. This is here, so we have 3/4, so 3/8 1 plus k here. All the m can be removed in this case, so that will be this. That will be a 2ga. Okay, is it 2ga? Is it 2? Yep, correct. So 2g, 2ag then, because all the thing can be simplified. And then the 4 here. All right, there's another 4 here. Let me see. It should be 1/8. Sorry, just let me change that. It should be 1/8. 1/8 ag. So the a is here, gone. So 4 here, 1/8. Yep, correct. There you have it. And then from here onwards, okay, from here onwards, we will have to plug in our substitute of v here, which is the same as u over 1 plus k. Okay, u equal to, and then our u is this one here, okay, which is the same as this one here. Let me see. It's 1 plus k. The u is 4 over 3 ga square root there. So if you square this, we can cancel off the number first. So therefore, if you square that, if you square this, we will get 1 plus k square, and then 4 over 3 ag equal to ag. Okay. So from here we should be able to get all the AG cancel off, the 3 cancel off. So therefore you have only 1 plus k is equal to a 4. Therefore k is equal to a 3 there. Now that will be the value of k. So I'd just like to remind you, if there's a collision involved, we must use conservation of momentum. And then I do recognize that the wording that they are using is a bit confusing. So just to try to clarify, at a point C in the subsequent motion, I think when they mean at the point C, so that's how they define your initial speeds there, right? I hope that that is clear. We can move on to the last section, B, for this question. Right, we have reached the last sections for this question here. Okay. Now at the point C, the horizontal surface become rough. Okay, so at point C, the horizontal surface become rough with coefficients of frictions mu there. Right now, between the combinations of the particle and the surface. So the decelerations of the combined particle is equal to 9 over 20 g there. Now k that we have obtained in our previous section is 3 here. Right. Now the combined mass, okay, now just to show you again, the combined mass, so you can see that they collide, they compress, okay, so they compress there, and then the combined mass now is actually 1 plus km. Now the k is 3, so therefore the combined mass will become 4m then, right? Now since it's compressed this way, so therefore the frictional force will be acting these directions here. The normal is given by this, and then there is also a compression given by the spring itself. So the compression is acting this direction. So we just label that as tension itself, right? Okay. So the deceleration, yeah, up to you how you want to see that. So the decelerations will be since it's compressed these directions here, the deceleration is given by negative 9 over 20 g there, right? Okay, we are pretty much ready. The other thing we need to know is the F is actually equal to mu r here. Okay, mu r, whereby the r is the same as its weight. Okay, in this case is 4 mg. So 4 mg here. Or we can write down the frictional force is actually 4 mu mg here. Right. I hope that is clear at this point. Now, by using Newton second law again, so Newton second law. Okay, now the resultant force, you can see that the resultant force uh, is basically okay, so it's negative t plus f. Okay, because there is no force acting these directions other than acting in the opposite direction. That will yield the accelerations here, which is 4m negative 9 over 20 g. Okay, if I were to simplify this, that will be a 9 over 5. Okay, 9 over 5 mg there. Okay, negative of 9 over 5. Okay, and then therefore you will see that there will be a tensions plus F is equal to 9 over 5 mg. All right, and then tension. All right, now tension is given by 4 mg over A. All right, now it has compressed quarter, so the tensions will be a quarter here, right, plus the frictional force will be equal to this. All right, so therefore in this case if we try to simplify that, that is actually an mg, and then we should be able to get F equal to 4 over 5 mg. Now, knowing that the frictional force is given by this, okay, so knowing that the frictional force is given by 4 mu mg, then that must be the same as 4 over 5 mg. Therefore, the coefficients of frictions is equal to, coefficient of friction is equal to 1 over 5 there. All right, now that concludes our discussions today. If you like what you're looking at, do press the subscription button and then a notification bell to receive the latest video from me. All right, until I see you again, take care, everyone.